Welcome to Fizzics TWIST. This week in Science and Technology, the Australian science news podcast for the scientifically curious, both neophytes and crackerjacks alike. We are powered by Fizzics Education, leading science communicators in the education space. And it's our job to deliver exciting science content all around Australia. And what better way to do that than with a direct injection of science content straight into your ear holes. In this episode of Fizzics TWIST, in Huge If True, how much does a kilogram weigh? The answer may surprise you. In On the Green with Quill, the world's oceans are being eaten by something. But what? In Far Out with Duncan, a huge discovery under a glacier of cosmic origins. And a new fact of the week. Just to note that we are recording with a different microphone this week because our lovely company director and CEO, Ben Newsome, has taken our normal one this week because he's interviewing the one and only Dr. Carl. So if you're here from the Dr. Carl interview, welcome to Fizzics TWIST. Hey, Quill.
Yeah, Duncan.
How much does a kilogram weigh?
A kilogram?
Yeah, I think that's a pretty good answer.
Yeah.
But it has to weigh, like, something.
Yeah.
Right? Like, you have to be able to quantify it. You have to give it a number somehow.
Compare it to something.
You have to compare it to something. Exactly right. So that's what they originally did when they came up with the concept of the kilogram.
Okay.
And what they did, this is the French, back in the late 1700s, early 1800s,
Cool.
is they defined it as being pretty much like they took this piece of metal and they said, that's a kilogram.
Right.
Okay, it sounds arbitrary.
It does.
But you have to compare it to something in order for anything to make sense.
Yeah, you have to start somewhere.
You have to start somewhere. So that something that it weighs is basically like this chunk of what's called platinum iridium alloy.
Ooh.
That was actually created in 1889, so after they created the whole system. And that's housed at the International Bureau of Weights and Measures in France.
I didn't know there was such a bureau.
There is such a thing. So the kilogram comes from what's called the Système International, right? So SI.
International system.
International System of Units. So things like the kilogram and the second and what other
kind of measures of anything, I guess.
Measures of anything, at least, you know.
Because you've got to measure something in something.
Exactly.
In a unit of some sort.
Yeah, exactly. So like 12 rods to the hogshead, that's not SI units. We don't do that anymore.
Right.
But yeah. So,
one elbow to kind of halfway up my wrist.
Yeah, being a yard or something like that. Yeah, that's the one that's in France. That's called the International Prototype Kilogram.
Wow.
Goes by a couple of nicknames. One of them is Big K.
Big K.
Another one is Le Grand K.
Why K?
Kilogram.
Oh, right, of course. Yes.
Yeah. So what they did is they've got that one. And that one object is defined as the kilogram.
The kilogram.
It's not a kilogram, it's the kilogram.
Okay.
And they made a bunch of copies of this thing and they sent it around the world.
Okay.
Do you see where this is going at all?
Our kilograms might not be kilograms?
Yeah. They discovered a little while ago that the kilogram is actually losing weight.
So it's losing kilograms.
Yeah. That becomes a problem because now everything is out of whack because that kilogram is the kilogram, which means things that used to weigh a kilogram now weigh more than a kilogram. Do you know what I mean?
Well, if our kilogram suddenly is less than a kilogram, then everything is kind of in a ratio to that kilogram.
Yep.
Does that mean we all weigh less? So we've just lost some weight?
No, we would weigh more.
Oh, there you
That's
go.
That's the problem. Yeah, exactly. What's going to happen now is because they've realised that this is a huge problem, on Friday, which is tomorrow, at the time of recording, scientists from around the world are meeting at the General Conference on Weights and Measures in Versailles. The General Conference on Weights and Measures. What a party, right? It's going to go wild. It's going to go crazy.
Yeah, actually, you know, conferences go pretty crazy.
Do you think this one's going to go crazy?
You study hard, you party hard.
Yep. This isn't uni, mate. So
clearly never been to a scientific conference.
I haven't, actually.
Well, let me tell you.
Yeah.
It's a lot of fun.
So what they're going to do is they're going to vote on a new definition of the kilogram. Okay?
Ooh.
And rather than being tied to a physical object like it is now, it's going to be tied to a universal constant in nature, because all the other SI units are tied to a constant in nature.
Yeah, right.
So the second, for example, that is the number of vibrations of a piece of quartz or something like that.
So we want to link it to something that's not going to change.
Exactly.
Yeah.
Because the problem is, like we said, it has lost weight. It's lost about 50 micrograms, which is about the mass of an eyelash.
Okay. So not a lot, but when you're basing everything in the world on this, could be pretty important.
Absolutely, because then we don't know how much things really weigh. So it needs to be a constant thing.
Yeah.
So what they're going to do is they're going to redefine it, and that's if the vote passes, which it's expected to. They're going to affix the definition of the kilogram basically to something called the Planck constant. Now, Planck constant is far too complicated to explain. This would turn into a 3-hour podcast if we did that.
We'd have to do a bit more research too, probably.
Yeah. It's basically...
Planck's constant has to do with light, doesn't it?
Yep, light. It's a quantum mechanics thing.
Yeah.
So it basically is the amount of energy a photon carries with the frequency of its electromagnetic wave.
Which basically is too much for us to explain in this episode.
Far too much, yeah. So it was named after this physicist, Max Planck. So, like I said, the kilogram's the only one that's still defined by a physical object. So something like the meter, for example, that's now tied to the distance light travels in a vacuum in 299,792,458th of a second.
Look, that's what a meter is. It sounds more accurate to have it associated with something like that, as opposed to a rod that's losing eyelashes all over the place.
Exactly, yeah.
And now I have this image of a rod with these beautiful big eyes fluttering its eyelashes and going, I just lost an eyelash and now I lose my job.
Yeah. There you go. And the second, it wasn't quartz, it was atoms in an element called cesium. Right? So they're constant. No matter where you are in the universe, that will never change.
Samesies.
Ever. Certainly not losing weight. I mean, I could stand to lose a little bit of weight personally, but hopefully a bit more than an eyelash. So, what I thought we would do, given that this is happening, is talk about some other units.
Okay.
Some of which are quite funny.
Okay, let's hear them.
Here's one. We've got the beard second.
A beard second?
Beard second.
Is this how long a beard grows in a second?
Is a unit of length inspired by the light year. Okay. But it's kind of more applicable to extremely short distances, right? So they use this in things like integrated circuits. And integrated circuits, like what computers are made out of, basically.
Sure.
The beard second is defined as the length an average beard grows in 1 second.
Legit?
Yeah.
I was right.
How good is that?
Beard second.
It doesn't actually say how, in my notes that I've made, it doesn't actually say how long it is, but I'm assuming it's
what distance?
Tiny.
Next time someone asks me when I'll be ready, I'm going to say in a beard second.
No, but it's a length.
Oh, that's right. How far away are you?
From what? Oh, yeah.
Like
I'll be there in a beard second.
How far away are
I'm just 1 beard second away. I'll be there in 0.000. No, wait.
You're getting
there in 1 second.
Time.
Yeah.
Yeah.
There you go. Here's another one. The smoot.
Spell this for me.
SMOOT.
Nice.
Also a unit of length.
What's a smoot?
It's defined as the height in 1958 of Oliver R. Smoot. And
so measuring things in smoots now.
Yeah, so in 1962, he was a student at Harvard, and they measured Harvard Bridge, as a bridge at Harvard, in smoot units. And it was determined to be 364.4 smoots.
Cool.
Plus or minus 1 ear.
1 ear, one smoot ear.
1 smoot ear.
Because different people have different ears.
Yeah, so you know what's amazing about this is that Oliver R. Smoot himself later became the chairman of the American National Standards Institute.
Well, there you go.
And then the president of the International Organization for Standardization.
Good work, Smooty.
How good is that? And at the time, he was 5 feet 7 inches, or 170 centimetres, using SI units.
A good average height.
Yeah, pretty. Oh, it's actually kind of short.
I was thinking it was kind of tall, but that's kind of...
It's not. And what's really funny is that Google Earth and Google Calculator include the smoot as a unit of measurement.
Fantastic.
Because Google, man, they're just a bunch of nerds, really, a bunch of Harvard grads.
We love nerds.
Yeah, we do.
So, does this mean that my elbow to, so sometimes I'll measure something from my elbow to my wrist, or my elbow to my fingertip. Or it might be like, okay, this one's 2 elbows plus a hand. That's legit, because if a smoots is a legit one, then surely Quill's elbow is a legit one.
Could be, yeah. Only problem there being that the length of your elbow to your wrist probably changes a little bit from day to day.
But wouldn't smoots change?
Yeah, they would. Yeah, but it was that particular time,
okay,
within like a few minutes, that they measured 364.4 smoots,
okay,
the length of Harbour Bridge. Here's another one. A pirate ninja.
Excellent.
A pirate ninja is defined as 1 kilowatt hour per Martian day, or sol.
There's a lot of random units in that equation.
Yeah. So anyone who's listened to the special edition Mars Rover Magic episode knows exactly what a sol is. So have you seen The Martian and or read the book The Martian?
No.
Oh, it's a fantastic movie. You've got to see it.
I will put it on my to-read/watch movie list.
Definitely. So Andy Weir, who's the author of that book, basically said that he came up with this definition. I think he came up with this definition. But apparently Adam Savage, you know who Adam Savage is?
I do.
Yeah.
No, wait, I'm thinking of Fred Savage.
Ghostbusters. Oh, my God. The 80s heartthrob. Who could resist?
Wonder Years, man. You know I'm old.
Yeah. I wasn't going to say it, but... so Adam Savage said that the Curiosity rover team, which we've talked about on the special edition, at JPL references millipirate ninjas in their meetings.
Cool.
How good is that?
I feel like we should start measuring things in millipirate meters. Yeah. Ninjas.
But what do we have that could measure kilowatt hours per Martian day? I don't know.
We'll maybe future Duncan will think of something awesome.
Yeah, I think current Duncan could probably come up with an idea, like a generator that probably works in kilowatt hours. Yeah. Future Duncan, is that correct?
Pretty much.
Cool.
Cool.
Nice.
Thanks, future Duncan.
Oh no.
Oh.
How silly of me.
Damn.
Yeah.
We should have thought of that.
Yeah. So there you go. The kilogram, no one really actually has any idea how much it actually weighs. I should also mention, I said that there's like 7 copies around the world. Those have all been changing in weight as well.
And at the same ratio? Like, has everyone lost an eyelash, or is someone else lost like an eyebrow?
No, some of them have gained weight, and others have decreased in weight. So I saw a chart. You can look it up on YouTube. I might actually put in a link in the show notes to a video about this, because it's absolutely fascinating. But these things are kept in, they're like I said, platinum iridium, and they're kept in these incredible, like, hermetically sealed.
Yeah. Basically a special chamber that has like no air, kind of no special conditions, so that it doesn't degrade or anything like that.
Exactly, and yet they do. That's what's so confusing about it. But it's like, behind locked doors where it takes like 2 keys to open and all that sort of stuff, and yet they are still changing weight despite being kept in these incredible vacuums. It might
be all the stress from the secrecy.
Maybe. It's freaking out. I mean, if I was being used as an SI unit, I would probably freak out too.
Am I as tall as I thought I was?
Yeah. If I'm shrinking at 1 eyelash like a day, that's fine.
Yeah.
I'll still be pretty tall.
See how much hair I leave around the house.
Yeah, exactly.
I'm shrinking. Maybe that's why I'm so short.
No, I think there's other reasons.
Genetics.
Damn genetics. So there you go.
Interesting.
We will have finally a actual definition for how much a kilogram is, and then we can know how much we weigh for sure.
And we might all gain weight and all lose weight.
Yeah.
Cool.
What if I wake up tomorrow, once they've done the vote, and I'm like, I'm 120 kilograms or something like that?
Nothing but celery for lunch.
Yeah, exactly. Calorie deficits, baby. So there you go. That was huge if true.
Interesting. That's very interesting. And I never really thought about where measurements come from.
No one really does.
Just kind of go, this is how we measure this. But not like, when did we start measuring this like this?
Definitely. And a second is just like 1/60th of a minute. But
where does
how long is that?
Yeah, and you've got to define what it is before you can start separating out into little bits.
Precisely. And then that means that all clocks around the globe can be exactly synchronized and all that sort of stuff. Yeah. And satellites as well.
Cool. Which is really important.
It's very important.
All right, Duncan, are you ready?
To
be on the green.
With
me.
Yeah, on the green with Quill.
On the green with Quill. Right, I have a super cool story for you today.
Hit me.
It's really cool. The Earth, well, actually, not so much the Earth. The oceans in the Earth, are getting eaten. They're getting gobbled up. Being gobbled up by the Earth. Earth is eating its own ocean.
That makes no sense.
Okay.
Where does it go?
It goes into the Earth.
How did you find this out?
Google.
Okay. Dr. Google.
But it's right.
Harvard nerds.
So this is a kind of interesting story that's come about, and there's recently some new data published in Nature. So Nature is a really fantastic and very high level journal. So that's where scientists publish their articles in journals.
Pretty much only the best ones go there.
Yeah, and that's right. And so they're actually reviewed by other scientists to make sure that they're really good science, because you can't just be doing random science here and there. So this one's from Nature, which means it's good science. So it's actually got a lot of background to it, and it's, legit. And what's going on is the Earth actually is eating its own ocean. What we mean by this is the ocean is kind of disappearing under the Earth. And I know that sounds confusing.
Yeah.
I'll tell you what I mean. So we know that the Earth is the Earth, but it actually has a lot of layers. You knew this?
Yes,
yeah,
I knew this.
Of course. So it has a lot of layers, and part of those layers is our tectonic plates, and that is part of the outer layer of the Earth, which is known as the Earth's crust.
Yeah.
So basically imagine the Earth's crust, or the outer layer, it's kind of like the skin on an apple or something. And then deep down the apple you've got flesh, and then you've got seeds and all those different things, and these are all represent different parts of the Earth. So the crust is actually made up of like a jigsaw. So it's not just one layer like an apple skin. Imagine your apple skin was cut into lots of little pieces like a jigsaw that then fit together to make the whole crust.
But they don't fit together perfectly, do they?
They don't fit together perfectly, like if you've ever done a jigsaw for a second or third time. The pieces start to not fit together so well. Okay, especially if you've been eating, or someone's been helping you that's young, or your dog's chewed the pieces or something like this.
Don't eat the crust.
Don't eat the crust.
Not the Earth's crust. Not good.
So what's happening is these tectonic plates sometimes when they come together, what they do is they have what we call an earthquake-prone subduction zone. Now, that's a lot of big fancy words. What it basically means is bits of these crusts will go under each other.
Yep.
Okay?
So one goes over the top, one goes below.
Because you can't ram two things together and then they both just stay there where they are. So one will go under, one will go over. And when they do this, like you naturally think of it, it's actually going to draw some water down with it.
Right. It gets sucked in.
Yeah. Okay, so it's kind of sucked in or pushed down or whatever, however it happens. And as it's doing this, now you remember these crusts then come together and you've got one that's over top of the other one. But the one that brings the water down with it, you've kind of now sealed it back up again, in essence. So you brought that water down into the next layer of the Earth, or below the actual top surface of the crust, and into what we call the mantle, which is the liquid hot magma layer of the Earth. Cool.
Does it just boil off, or is there a way for it to just stay there?
Well, this is what part of what they've been kind of investigating and finding out, because we're not talking about a few drops that would just evaporate like they do if you flick some water in a hot pan. We're talking about millions and millions of litres of water.
Yep.
Okay, so a huge amount of water. So basically what they're finding is that there's actually 3 times more water going into the Earth than we actually originally thought there was.
Oh, so this is not a new discovery per se. So we already knew that some of it was going down there.
They knew some was going down, but it's a lot more than they actually thought.
Yeah.
But what is kind of new is that they always thought some went down, some came back out, some went down, and it was kind of even. So what they've discovered as part of this new part is that actually it's not even. There's a lot more water going down into the crust, down below the crust, than there is coming back out. And so it comes back out through things like volcanoes. So when we have a volcano, these volcanoes are often in these locations where the crusts meet, where the plates meet, and then they have water in them as well. So there'll be water in them, whether that's in the form of steam or whatever. But what we're actually finding is there's nowhere near enough water coming out in those to account for how much is going in.
Right.
So where's all that extra water going?
Yeah.
Because we're not losing water on the surface. So it's got to be somewhere how it evens it out.
Yeah.
And so what they're discovering is they can actually listen to the way that earthquakes travel.
What?
Yeah, it's pretty cool. So they listen to the way that earthquakes travel, and they've done this by listening to earthquakes that are happening in the Mariana Trench, which we know is the deepest part of the Earth.
The deepest known part, anyway.
The deepest known part of the Earth is actually 10,994 metres deep.
Good Lord.
Which is, wait for it, 984 football fields deep.
Now you're speaking my language.
Yeah,
that makes sense.
Now that doesn't sound like a lot when you're thinking across the surface of the Earth, but when you're talking into the Earth, that's a lot.
It's almost, 11 kilometres straight down.
Yeah, exactly, which is really, really deep.
You know they've actually gone there in submarines?
It's really cool.
Yeah, and there's some weird stuff down
there. There's some weird, creepy animals with light bulbs and various other strange things going on.
Awful teeth.
Yeah. Ugh. So what's going on is this research is helping understand what's called the deep water cycle. And this is basically what's going on with the water on the Earth, how does it move between parts of the Earth, and what happens to it as it moves between these places. And the contribution of this understanding this cycle has lots of different things that we can learn from this. So basically, what is happening is the water can also be stored basically in a crystalline form, which is like a crystal of water. And it does this when it forms into minerals. So a lot of minerals would be hydrated minerals that have lots of water in them. It can also have what we call, I guess not hydrated again, but kind of water-filled, I guess, fractures in the crust as well. And when we listen to earthquakes, we get an echo from them.
Yep.
And when we listen to that echo, the speed that it travels, so its velocity, is actually slowed down when it passes through area where there's water.
Oh, okay.
So you can kind of listen to it, and it will be travelling at a certain speed, and then it will slow down, and then it will speed up again. And what you're doing is you're kind of understanding how much of that is passing through water. And this is below the Earth's crust. So you're listening to kind of what water is going on under there.
Yeah. That is super clever.
It's pretty weird.
Really clever.
But really cool.
But we're not actually losing any amount of water that we need to be concerned about?
We're not, but we're not losing water, right? We can't just lose water.
No, it doesn't go any... Well, yeah, it doesn't disappear from the Earth entirely. It's still on Earth or in it. So
the really interesting part of this is what they've actually learning about this is that there must be another way that water can move through the layers of the Earth. So it was always just assumed it always came out as steam and whatnot coming from the mantle up through the crust in volcanoes and stuff like that. But now we're realising that there's way more water going under than there is water coming out. So there's got to be another way that it's coming out, or else our whole world would kind of be losing water and we'd be seeing it.
Yeah, I see what you mean now. Okay, so it's still part of the sort of greater water cycle, if you can call it that.
So it's getting out
don't know
some other way.
Yeah.
So like,
what is it?
It's like seeping out through something or something. They don't know, and this whole idea has kind of opened up a new way of looking at the way that water can move and the deep water cycle and how water moves from different layers of the Earth.
Well, what about if it just goes back up when tectonic plates move again? Is that possible?
It's possible, and there are some spots like where it kind of you can see like really hot water will bubble and whatever, but they would still kind of count those as when water's coming through a volcanic activity, I guess, because there's something more happening there, like whether that is like seeping up through the layers of the crust just in general rather than like kind of pouring out through these tectonic plate boundaries or something. I don't know. They don't know.
But we don't know yet.
We don't know.
Okay, well, it remains to be seen.
Yeah, who knows? Might just seep through like it does when you soak up a sponge.
Yeah, but it's rocks though.
Yeah, no.
Are rocks spongy? I don't think so.
Maybe.
Have you seen that photo of someone diving in between two tectonic plates?
No.
Oh, it's crazy. I'll put it in the show notes for you.
Is it legit?
I think it's legit. So there's basically like these two sort of huge cliffs of rock underwater that are probably like 10 metres apart, maybe. And apparently they're two tectonic plates that are just about to collide or that are sitting right next to each other. And this diver goes right in between them and dives. And I was like, well, I hope there's no earthquake right now because you're going to get smushed.
Or any weird, creepy animals with, like, magma heads
they
and light bulbs.
I'm fine if they die.
Giant squids.
Yeah. You know, if you bring up those creatures from really deep, like in the Mariana Trench and the Challenger Deep and stuff, if you bring them up, they die instantly.
Yeah.
Because they're used to the pressure down there. Yeah.
But they probably could survive in space.
Do you reckon? No, that would be no pressure. Wouldn't it?
Yes.
Yeah.
Backwards.
Yeah, the opposite of that. Yeah. So they're going from massive pressure to no pressure at all.
That was a really dumb thing to say.
It wasn't really dumb. They would literally explode if you did that. That'd be kind of cool. I'd love to see that.
Duncan, we don't talk about blowing up animals on the green part of the show.
Take it to another segment.
Not environmentally friendly.
Okay, well, that's actually a pretty good transition to Far Out with Duncan.
Far Out.
Should we do Far Out? Far Out!
Far Out.
With Duncan. Should we do that now?
Yeah, far me out.
Do that right now. Okay, so this does involve exploding animals.
Duncan.
In a weird way.
I feel like we needed a transition from the green part to exploding animals.
That was it. That was the segue. Yeah. Okay, so this paper has come out in a journal called Science Advances, talking about how there's some weird stuff happening out of a place called Hiawatha Glacier.
Ooh.
Now, that was my first attempt at pronouncing that, so I hope it went all right. So being a glacier is basically this huge, slow-moving sheet of ice This is more than a kilometre thick, and it's in Greenland. So Greenland is like northeast of Canada.
Okay.
As we know, Canada is really north as it is. So this place is...
Great place.
Real north, real cold.
Real north, real cold.
Yeah. So what they noticed, scientists, in particular this guy called Kurt Kier, I have no idea how to pronounce his name because it's...
Sorry, buddy.
It's very tricky. I think he's Danish. Yeah, anyway. So notice that water drains from the glacier not in a straight line as it would normally do, but kind of in this like semicircular pattern.
Cool.
So this gentleman, Kurt, I shall just refer to him as Kurt from now on, he's a geologist at the Natural History Museum in Denmark, in Copenhagen, along with 21 co-authors, thinks this is weird, they better look into it. So our friend Kurt gets in a helicopter, flies over there, starts collecting samples, being like, I think I can figure out what's going on. What he found is the reason this glacier is draining in that weird semicircular pattern is because underneath the glacier there is a giant crater.
Ooh.
Yeah, underneath the glacier.
Cool.
31 kilometres wide.
Whoa.
Yep.
That's big.
So what causes a crater?
Space junk.
Sometimes. What's another thing?
Space rocks.
Yeah, space rocks, so an asteroid,
Yes.
right? To cause this 31 kilometre wide crater, the asteroid that hit it must have been at least 1.5 kilometres across. Now, at this point, you must be thinking, well, how many football fields is that?
Yeah, of course.
The answer is 16. It's 16 football fields across.
Still pretty big.
Big asteroid, right? The thing is, it was made of iron.
Ooh.
Yeah, so it's a big buoy.
It's a big metal,
buoy.
massive thing that's smashing into the earth.
Yeah.
Sort of like what
into
happened when we
Greenland.
wiped out the dinosaurs.
Exactly. We'll come to that later. Apparently this thing weighs 12 tons. Seems real light to me for a 1.5 kilometre thing of iron to weigh 12 tons. Yeah.
That doesn't seem...
Doesn't
but
seem
you
quite
know
right.
what?
What's that?
A kilogram's changing.
True.
So
Who
that
knows
could be
how much
inaccurate.
it weighs? Exactly.
It could be a whole eyelash off.
Exactly. This
12 tons plus an eyelash.
31,000 eyelashes.
12 tons.
So yeah, some researchers on this team basically believe that the asteroid struck at a pretty crucial moment, roughly about 13,000 years ago. It could go up to like more than 100,000 years, but they're saying maybe about 13,000 years ago, which is just as the world was thawing out from the last ice age. So that would mean it crashed into Earth when mammoths and other large animals, megafauna,
Still hanging out.
where they were basically declining, and people were spreading across North America. So that was where the exploding animals thing came in, by the way. You know, your asteroid comes in.
Well, that's okay. That's not intentional exploding.
Yeah, exactly.
That's space
It's
junk
fine.
exploding things.
So this explosion, when it hit, would have been absolutely massive, right? Colossal. Would have been like the energy of 700 nuclear bombs.
Whoa.
And observers who were like, you know, up to 500 kilometers away basically would have had this like shockwave hit them, and then this like monstrous
That's crazy.
thunder noise and stuff, and then winds that blow at the speed of a hurricane.
I don't think we
Crazy.
can ever actually imagine how big an impact like that is. If
No,
you haven't
it's
been
never
in
happened
something
in
that's-
our sort of modern
Yeah.
times. But yeah, that's not all. This is the part where it gets really interesting.
Okay.
So other scientists have been looking for an explanation for something called the Younger Dryas. The Younger Dryas is a 1,000+ year long cooling event due to disrupting currents in the Atlantic Ocean.
Okay.
Right? So they know this they suspected that this was happening, but couldn't really say why.
No reason.
Guessing that it was probably an asteroid that caused a disruption in the currents.
But they hadn't found any craters.
Yeah, so they're thinking, hold on, we haven't seen any craters, so like this is just total guess at this point. This Younger Dryas, this sort of cooling event, they think it's due to an asteroid that also would have lit wildfires all across North America.
Yep.
Greenland technically, I guess, is part of North America, that would have caused the extinction of like heaps of large mammals, and also of the Clovis people, who were native to the area and hunted mammoths.
Also, I don't know how long ago did the different landforms separate?
Oh, that's millions
That
and
was
millions.
Okay,
Yeah,
just checking.
more dinosaur
I
era.
should know that.
Yeah, this one's 13,000 years ago,
Right,
so
that's not
everything's
that
pretty
long
much the
ago.
same. Yeah.
Okay, cool.
So yeah, you put two and two together. We're looking for this asteroid somewhere in the area. Here's this massive asteroid. It's probably the one that did this, right?
Cool.
So there's the answer.
Yeah. Okay.
Pretty neat. So I thought, good opportunity to talk about other asteroid impacts.
Okay.
All right, here's some massive ones. the Vredefort crater, also my first time attempting to pronounce that. I think it went
Cool.
all right.
That went all right.
2 billion years ago,
Okay.
basically in South Africa.
Oh, okay.
The crater was declared a UNESCO World Heritage Site in 2005.
I've never seen an asteroid crater.
Neither have I.
Put that on the bucket list.
Yeah, let's do it. Maybe we can get work to pay for it.
Yeah.
How it goes.
Research.
Yeah, exactly. Another one called Sudbury Basin, 1.8 billion years ago. That was in Canada. The Acraman crater in South Australia.
I've never seen it.
Yep, neither have I.
Is it still there?
580 million years ago. Yep, it's in Lake Acraman. And it's about 56 miles, 90 kilometres across. And then, here's a good one. Oh, this is going to be terrible to pronounce, but Chicxulub crater.
That one I know.
Which one is that?
That's the one in Mexico.
That's the one in Mexico.
I believe it's pronounced Chicxulub.
Chicxulub?
I think so.
Okay. My bad.
I could get that wrong. That could be me, like, Chinese whispers down from someone else is the way they pronounced it, but yeah.
So that one, 65, 66 million years ago, 200 kilometres wide.
And that was the one that demolished the dinosaur.
Absolutely. Yeah. Basically the entire Earth into this massive sort of ice age because...
Sent up a huge amount of dust.
Yep.
Blocked out the sun. Changed the way that all sorts of things happened on the Earth. Killed all the vegetation. Killed all the vegetarians. And then killed all the meat eaters.
Exactly.
Progression.
And only the birds survived. Or rather, tiny dinosaurs survived and became birds.
Tiny birds.
Tweet, tweet. So there you go. Massive, massive asteroid discovered under a glacier.
That's pretty cool.
It's pretty cool.
I'm interested to hear what else comes from that.
Yeah.
Because once you learn something like that, then suddenly new stuff starts popping up out of it as well.
Absolutely. Yeah. So I, wonder if this Younger Dryas theory will actually be confirmed. Because at the moment they're just kind of like,
Could match.
I think that's basically about right.
Pretty close.
When you look at two puzzle pieces and you go, yeah, I reckon.
Sort of the same.
Yeah.
And then you realise one's upside down and they don't actually fit together.
Yeah, I'm not good at puzzles.
I love puzzles.
Well, I think we've got one more little segment there.
We do.
What's it called?
This one is the Fact of the Week.
Fact of the Week.
Fact of the Week. Fact of the Week. All right, so I've got a fact for you, Duncan.
Mm-hmm.
And it's sort of related to what you were just talking about in an offshoot kind of way.
Wow, so many fantastic segues.
I know. It's like we planned it, but we actually did it. That's the best bit. All right, are you ready?
Yeah.
Water can boil and freeze at the same time.
The triple point?
The triple point.
Yay!
Oh, you already knew
Yay!
that.
The triple point.
That's heartbreaking. I was really excited.
Does it happen? Sorry, I ruined it. Tell our dear listeners about the triple point.
So, the triple point happens when the temperature and the pressure is just right for all three phases, gas, liquid, and solid. So the phases are obviously whether we have got our molecules all really close together and a solid, or they're wiggling past each other a little bit like a liquid, or they're full of energy and wiggling up as much space as they can, which is gas, of course. And this basically means for them all to be right pressure and temperature, and then they can exist in what is called a thermodynamic equilibrium.
Nice.
Which basically means you have all three states existing at the same time. They're constantly going from one to the other, but they're doing so at a rate which means you always have the same amount of all three of them.
Very cool.
I've
seen a video of this and it's weird.
Yeah.
It's very weird because it's like the ice starts boiling and stuff like that. So strange.
Crazy stuff.
Now, the temperature that this happens at, correct me if I'm wrong, 0.01 degrees Celsius.
I think you are correct.
Only temperature that can work.
Pretty amazing.
Yeah. Future Duncan, is that correct?
Nailed it.
Oh, nice.
And what about the pressure that it has to happen at?
Is it a pressure of zero?
I don't know.
0 atmospheres? I'm pretty sure they have to do it in a vacuum.
Maybe. I think so.
Yeah.
I probably should have researched that more thoroughly.
That's okay.
I just thought it was cool and I got sidetracked.
I just went down some weird, YouTube rabbit hole at 1 a.m, probably on a school night, going, wow, that's amazing.
Cool.
Triple point of water.
So there you go.
Yeah.
It's not as exhilarating as I thought because you already knew.
I really ruined the surprise on that one. But the listeners, you just blew the top right off their heads.
I hope so.
Yeah.
Wait, I've got another one. This is not science related, but this one blew my mind. Mm-hmm. This is not going to be a fact for you because you don't have girl hair. But bobby pins, they actually go in the other way around. This won't blow your mind unless you use bobby pins. For those of you listening out there, bobby pins actually go with the sticky up bit into your hair, not the flat bit. So ladies, or people with long hair out there, if you're listening, I hope that one blows your mind more, because it blew my mind.
Really saved the day with that one.
See, you didn't know that one.
I really didn't know that one.
I don't think you ever want a bobby pin.
I have worn bobby pins back in, my younger days.
Well, there you go.
In my experimental phase in college. But yeah, I mean, just to bring it back to the science for a second.
Yes.
The fact that something can exist in 3 phases at once,
yeah,
solid, liquid, gas, at the same time, is pretty
awesome.
incredible.
Yeah, it's very cool.
I wonder if there are any other elements that can do that.
Yeah, there probably is.
Let's leave that open.
I mean, if water can do it, which isn't an element, but it's compound, but that's okay. If water can do it, then there must be other things that can do it. I bet there is, and I think that's what they use. I think you can use rotary evaporators to do that, which is basically like a vacuumed contained glass bulbous container that is connected to a vacuum and it rotates. So what you're doing is you're cooling it, it's in a vacuum all at the same time. And I think I believe this is how they do it with the water as well.
Oh, wow.
So I would imagine that there's different temperature and different pressure settings where you could also do it with different kinds of substances.
Dr. Quill, everyone.
Every now and then this random, that random PhD that I got actually brings out useful information.
I just go on YouTube.
I'll take your YouTube and I'll see you 4 years in a lab alone.
Just got one-upped. Well, fair enough,
I'm sure mine costs a lot more. Actually, you know what? That is not true, because in Australia you don't have to pay to do a PhD.
Really?
Because at this point in your career you are an asset to the community to be learning
that. That's fantastic. But Masters you have to pay for.
Masters you do pay for.
Which is a real shame.
Yeah. Well, there you go.
There you go. I think that is a wrap on Fizzics Twist for this week. Do you think that's the case?
Yeah. I think we've learned enough for one day.
Excellent. Well, don't forget, you can also listen to the Fizzics Ed podcast, hosted by company director, CEO, and all-around nice guy, Ben Newsom. Particularly, check out the episode in which he interviews Dr. Carl.
And I believe he's giving away some signed copies of Dr. Carl's new book.
He definitely is, and I'll be honest, I rifled through that book. We should have pilfered it for Facts of the Week.
I know, and you know what? We're not allowed to win it either, which I was a bit disappointed about.
No, I know. Entering in a fake name or something. Hello, my name is Brian Cox. No, damn it.
Brian Cox.
Yeah.
Oh, dear.
So there we go. If you want to check out more of us from Fizzics Education, you can go to fizzicseducation.com.au. That is Fizzics education.com.au. And
don't forget to rate us on iTunes if you're enjoying what we're doing. That'd be great. Helps us out. And let your friends know.
Yeah, we want to reach as many people as we can. All right, see you next time.
Until next time.
Bye-bye.
Bye.